All right, so what?
Where's the
Under the handouts and lectures? Somebody else able to access it? Okay, so yeah. All right, just making sure it is, that I haven't made another error. Okay. So lecture 13 slides are located on the handouts and lectures. So last time we started node voltage. We're going to go over node voltage again, and then we're going to move to the next topic, which is superposition. A couple of other announcements before we start into the lecture materials. So next week, you're going to have a guest lecture. For those that have been going to the supplemental instruction sections, that's the same graduate student that will be here. She's great. You'll go over next week superposition and Thevenin, and also do some reviews and address any questions that are there. As far as due dates, I'm still having weird issues, it seems like, with Canvas. So it was due last night to have the Unit 1 feedback. So if you haven't done that, still turn that in. I'll accept them up to Monday. So go ahead and do that if you didn't notice that was there and a due date. It is due. It was due yesterday, but I'm extending that because some of you still are not seeing that. So hopefully this next week I can figure out the issues with Canvas and we can make sure everybody is able to see all the due dates. So I'll send out an announcement once I think it's fixed, and then you guys can check and please get back to me if you're like, no, I don't see that that's coming up and I know it's a due date. So hopefully that will get fixed. And then next week on Thursday, you'll have a discussion and the homework. The homework will be node voltage, superposition, and Thevenin. And then Thursday and Friday, I'm going to open up the quiz for 2 days to allow you to have a little bit more time. So Thursday and Friday, you'll have a quiz option to complete it, and it will be on the node voltage and superposition. Okay? All right. Any questions about upcoming materials? Okay. All right. So node voltage, so much fun. All right, so the goal of today is be able to look at a circuit and say, this is the node voltage equation for this circuit. So we want to be able to just look at it and write that equation right away. So that's one of the goals. The other goal is to apply the superposition technique when you have more than one source in a circuit. So this is the other thing that we're going to go over today, or the other technique that we'll go over today. All right, so node voltage. Thought I had copied it over. I guess I did not. So node voltage steps. Okay, so the first step, identify all your extraordinary nodes. So that's going to be your first step. The next one is to define ground, if ground is not already defined. Third step, assign all variables to each of those extraordinary nodes. And that means that there's a voltage at each of those nodes. Then you're going to write the node voltage equations for each node in terms of that node voltage variable. And then you're going to solve the system of equations for the node voltages. Okay, so let's look at this one. This is already labeled, so each of these is an extraordinary node. So this one, and this one, and this one, and this one. All right, so we have our extraordinary nodes. So 3 extraordinary nodes and ground, so 4 total extraordinary nodes. Ground is already labeled. So I'm just going to arbitrarily pick V1. So picking V1, I want to write that node voltage equation. So as we saw last time, you can write elements in a branch in any order. So we can swap them around. Here we already know the node voltage at one end of the resistor and then at the other end of the resistor. So on the two sides, on the top side we have V1 and on the bottom is ground. So anyone want to take a stab at this current. How would you write that current as far as a node voltage? Go ahead. Yes.
V1 minus 0 over 2.
Correct. Great. What about this current is going to be what? What's this current going to be?
-4 amps.
Thank you. Yep. So -4 amps when it's drawn out of there. And then this one. Good.
V1 minus V2 over 3.
Correct. Okay, so then we're going to sum all these three out of that node. There's 3 wires off of it, so we have to have 3 terms. So we have V1 minus 0 over 2 plus V1 minus V2 over 3 minus 4 amps equals 0. Okay, any questions about writing that equation? So this is the node voltage equation at V1. So take a second to write for V2 and V3 nodes. So V2 and V3 nodes. And then once you get those, you can engage if you want through the poll, which I'll also get started. If you want to work with your neighbor, go ahead and work with your neighbor. If you don't know your neighbor, just introduce yourself to your neighbor.
Video with flag behind it, I was like, oh, that. Might start trying that.
Okay, so this, at V2, I can define these all going out, and then I know that this one is going to be V2 minus V1 over 3. This one is V2 minus 48 over 2. And this one is either IX, or if I write it in terms of the node voltage, is V2 minus V3 over 6. And then summing those, I get the V2 minus V1 over 3, V2 minus 48 over 2, and V2 minus V3 over 6 equals 0. So that would be my node voltage for node V2. And then at V3, if I put all those currents out, the bottom current is V3 minus 0 over 4. This is going to be a plus 4 amps. And then the green arrow here is going to be V3 minus V2 over 6. Or I can just define the IX, which is in the direction of V2 minus V3 over 6. And then I can say it's a minus IX, or I can write that, so minus IX would be V3 minus V2 over 6. So whatever way you want to write that, it would be the same equation. I'm going to put it in terms of the nodes though. So V3 minus V2 over 6 plus 4 plus V3 minus 0 over 4. So now I have 3 equations, and I've got 3 unknowns, V1, V2, V3. So from here, you can either algebraically solve this. So options to solve. This is called simultaneous equations. So one option is algebra. Another option is called, trying to remember how I put these in your notes, Gaussian elimination. Elimination. So this is something, I think typically it's usually done in like Math 2250. But you may also see it in another math class, depending on which math pathway you take. Another option is to use an online calculator or your own calculator. And that's probably going to be the easiest one to do. So to set that up into a calculator, you're going to use what's called a matrix. Have you guys seen matrices yet? Seeing some people yes, some people are no. Okay. If you have not, what math, if you don't mind me asking, what math are you in? Which one? Left, to your left. So Calc 2, you haven't seen it yet. And you have seen it, and what was your last math?
My last math was
Calc 3. So you saw it in Calc 3 or before?
Before.
Before
Just in high school.
in high school. Okay. Who else said yes?
Yeah, I saw it a lot in Calc 3.
Okay, so you did see matrices in Calc
Yeah.
3. And you said no. Oh, wait, Calc 3. A tiny bit. Yes.
2250, we have, there was units on it.
Okay. So it is pretty much Math 2250. That was what I was thinking was the main place where you're going to see the matrices the most. So a little bit maybe you'll see in Calc 3 if you're not there yet. So I'm going to show you how to set up this system of equations and then how to use either a calculator or an online calculator to just solve it. This is also could be through MATLAB. If I can spell today, MATLAB. I think I'm a little dyslexic. Okay, so how you write this as a matrix form is that you define your variables. So here we have V1, V2, and V3. So the variables go in a column matrix as V1, V2, and V3. And before that is going to be this notation. So the notations of the big brackets are matrices. And then I'm going to have a matrix on the other side of constants. So then I define, so once I've defined this V1, V2, V3 variables, I'm going to look in each equation. So my equation 1, this is going to be my equation 1, this is going to be my equation 2, and this is going to be my equation 3. So they are going to line up just like that, equation 1, 2, and 3. So for equation 1, I'm going to note where all the variables are for V1. That's going to be in this first column. Actually, I'm going to do it from below. V1 terms. Second column is going to be the V2 terms. And the third column is going to be V3 terms. So in this case, I have V1 over a half and V1 over a third. So this is going to be a half plus a third. Then I have V2, and that's going to be a minus 1/3. So that goes in the second column, minus 1/3. And then I don't have any V3 terms in this one, so I put 0 there. And then I have a constant in there of minus 4. If I take that over to the other side, that becomes a plus 4. Does that make sense? Okay, let's do it for the second one. So the second one, I look at V1 terms. So I have a minus 1/3, and that's it here. So minus 1/3. I have a 1/3 V2 and a half V2 and a 1/6 V2. So I'm just going to write those out just like that. 1/3, 1/2, 1/6. And then I have the V3 term of a minus 1/6. And then a minus 48 over 2 becomes a minus 24, and I take that over to the other side for a plus 24. And then the third line, I have no V1 terms, and then I have a minus 1/6 for the second term. Plus 1, oh wait. Yeah, minus 1/6. And then for V3, I have 1/6 and 1/4. So 1/6 plus 1/4. And then I bring over the other 4, that becomes a minus 4. Okay, questions on creating these matrices? Yes.
Where does the 24 come from?
Minus 48 over 2, that's 24. And then I brought it over to the other side to be plus 24. All right, any other questions? Yes.
I don't understand what the terms on the left have to do with the terms on
So let me just rewrite this. So I'm going to combine all the V1 terms. So this can be rewritten as 1/2 plus 1/3. And then a minus or a plus V2, and then it would be a minus 1/3.
Please scroll this.
Oh yeah, you're not seeing that, sorry. So I combine the V1 terms, so I have a 1/2 and a 1/3. I combine the V2 terms, so it's V2 and then it's a minus 1/3 there. I have 0 plus V3 times 0, and then I bring over the constant over to the other side, equals 4. Do you follow that algebraically?
Yeah.
Okay, so from here, all I'm doing then is bringing down the V1 terms. So that's in this box. You can see it's the same. And then I bring down the V2 term and the V3 term. I'm just not putting the variable next to them. Instead, I'm writing it in this, what's called the matrix form. So I leave off the variable name and I just put the constant in those locations. And then the one on the other side is the values that are whatever on that right side. So in this case, it's a 4. And that's the constant. So I just did that for each equation. So I have 3 lines in this matrix. And that's the same as, I just looked at the equation and wrote them, but you can rewrite them like this first and then put it into matrix form. Does that make sense? Okay. So some of you, your calculators, you can just plug in the equation itself and do 3 equations and then look up how to solve on your calculator, just solve for simultaneous equations. Some of you will need to put it in matrix form first and then solve the matrix. You'll have to look up your own calculator and the capability of that, or what you can do for an online calculator. So either way, if you put it into matrix form, what this ends up being is you call these variables like A as a matrix, and that would be, let's see if I can bring this down. So what you do is you call these matrices some variable. So this would be a matrix A, would be this one. This is going to be your X as your unknown is equal to B. And so you have to find out from whatever you're using how to put in that matrix in whatever form it needs. In MATLAB, it would look like A is equal to a left bracket, and then you would have 1/2 plus 1/3, and then you would do a comma in between each of these, or a space, it will take either, and then you use a semicolon to denote the next line. So this would be -1, and it would look, I'm writing this like this, but it would be -1/3, so it's going to look more like that. I guess I should write this out more like MATLAB. Oops. This 1/3. And then you would define B as this one, which would be 4, and then again the semicolon denotes line. So the semicolon 4, 24, and then -4. When you hit return on MATLAB, you'll see the whole matrix, so then you can double check that it is actually correct. So then in MATLAB, all you have to do, which is really nice, is that you just say A is equal to inverse A times B. And that gives you your answers. And then it will come out in the form that you had of V1, V2, and V3. And that's all that you have to do for that. So if you're going to use MATLAB, great, just get used to using it. If you're going to use your calculators, get used to using your calculator to be able to solve. Whichever method you want to do. And then the answers should end up coming out. This is 3-9. Should come out as V1. So use this as an exercise to determine what tool you're going to use to solve these. I don't recommend algebra because people usually make mistakes in algebra, so I would use something that is more reliable, but you're welcome to use algebra if you want to use algebra. On the Canvas learning material, I've put steps on how to solve and examples on how to solve algebraically, how to do them on MATLAB, and so you can use those. You'll have to look up your own calculator. There is one example for 1TI version calculators, so look at, yes.
So we can use MATLAB on like the exams, right?
Yes.
Okay.
Yep. So you can use MATLAB on the exam. So just get comfortable with whatever tool you're going to use. Get comfortable with using that so you know it's accurate.
Okay.
So the answer should be, so use whatever tool you want to use and then double check that you come out, that V1 does come out as 84/5. V2 is 30 volts. And V3 is 12/5 volts. So once you get these answers, you can then find, this was asking for Ix in this equation, or in this problem specifically, and Ix was the V2 minus V3 over 6. So that ended up being 4.6 amps. All right. Questions about these? Any questions? Okay, so I'm not going to expect you to do the math as much as I want to understand the concepts and being able to apply it, so that's why I'm letting you use things like MATLAB. Okay? All right, this looked like a pretty, this was a little bit more complicated circuit than we saw the last exam. So now you know how to actually solve a more complicated circuit. And it can have lots of different nodes, and you can still set it up the same way and then solve for all of those variables pretty quickly if you get used to this. So what you're going to need to practice is writing these equations and making sure you're writing them correctly. So lots and lots of practice. So let's do... Okay, so in this example, I went over last time that there's something called the supernode, where you don't have a resistor in the branch, so you have to write the equation slightly different. And so in order to do that, we do know that we can write this supernode as a voltage difference because we know the difference between there is known. So how would I write this supernode equation? Anyone want to try? So you're going to write it in terms of V2 and V1. Anyone? No one? Go for it.
Wouldn't you just do the same thing except for you would ignore the middle current?
So what would it look like?
So would it be, this one would be, so one of them would be -2, right? Or it would just be, yeah, -2. Because are we just doing the same thing?
So what you're going to do here is the current that goes in here also, it might be easier to see this way. If it's the same current, it goes in and then it splits down to Ix and that current. So what we're gonna do is summation of these four, and then we're gonna say that this one is gonna equal the other two. Does that make sense? So that would be how we would write the whole equation. We're missing one thing here though, too. What else are we missing here? Thank you. Ground. Where do we want to put ground? Okay, I like to put it at the bottom. Is it wrong to put it somewhere else? You can actually ground it somewhere else. You're going to find IX is going to be the same, but then some of your voltage from in comparison to ground may be different because your ground would be located somewhere else. Okay, so have our 0 volts, ground, and now we're going to write that equation for the supernode, yes.
How come on V2 there's going out of the 6 volts, it's going into it? I thought they were supposed to go like, into each other.
Okay, I'm going to redraw these. Okay, so I'm going to call this temporarily IX. No, IX is already there. I1. So what I noticed from I1, and I'm going to call this just I2. I'll call these I3, I4. So last time I showed that I1 is equal to IX plus I2, or I could say I1 is equal to, well, the other one would be, let's see, they all go out. I1. So the left-hand node would be this summation, and I1 could be defined also as I4 minus I3. So to write those equations, we would need to know I1, but I1 can't be defined as V2 minus V3 over a resistance because there's no resistance in that branch. So what I said to do for these instead is combine these two, and we know that these are both I1. So we can equate them. So then we can say that IX plus I2 is equal to a minus I4 minus I3. And rewriting that is just pretty much the summation of all of those as they're defined as going out from that node. So we can just use this one instead of writing the intermediate ones. So then we could just say, because I kind of know, I mean, you can write them still with I1, but then you'll have to substitute in I1. So it's just an extra equation. So whichever way, do you guys want me to write it with I1? Is that less confusing? No. Or just write it as one equation? Just one equation? Okay. All right, so then we have to find like I3, I4, I2, and IX. So anybody want to do that? What about I4? Go for it.
Is that just gonna be V1 minus 0 over 0.5?
Yep. I3. -2, thanks. Yep. -2, and then I1, we don't know, so we would have to leave it as I1, or we can just skip I1 and write I2 and IX as the one equation. So I2 is going to be what? Correct. And IX? Go for it.
V2 minus 0 over 0.5.
Correct. I'm just going to stop writing the 0, but it is correct to have the 0 in there. Okay, so there's our equation for the supernode. But as I said, we skipped that I1, so we have to write another equation for that. So this is the extra step for a supernode. Is to write the voltage difference. So you look at the positive side and then you subtract off the negative side. So you would start with V2 minus V1 equals the 6 volts. So you take it from the positive side first. So that variable on the positive side is V2. So that would be our extra equation. Then we have the V3 node. So we have this current, and this one. So that equation is going to be plus 2 plus V3 minus V2 over 0.5. And then a minus 4 equals 0. And so we have our set of 3 equations. So this is our third equation, our first and our second equation. So we would set it up again in matrix form or just using your calculator. And I'm going to give you the answers and do use again as an exercise to find these. So V1 is a minus 2 volts. V2 is 4 volts, and V3 is 5 volts. And then if you want to find IX, knowing now V2, what is IX? What would be the equation for IX? If you can see that. So IX is here.
Would be 4 over 0.5.
Correct. So it would be 4, which is V2, which equals 4 over 0.5. And that ends up being 8 amps. So knowing these voltages now, you can find any current in any of the branches. How would I find the current in I1 though? I can't use just the node voltage to find that one. So how would I find I1?
KCL?
Okay, good. So can't find I1. By the current expression. I don't know, that doesn't make sense. I'll just put find I1 by a KCL. So this will include that you will need to have IX found, or not IX, I3 and I4. Or you could find, well, yeah, you could find IX we just found, so you would just find I2, or you could find it by knowing the I3 and I4. So you would use those KCL ones to find that one. Does that make sense? Okay. All right, so now we have the techniques to be able to find these with the node voltage. So it's a very powerful technique. Again, this is typically the one I use to solve all circuits. It's usually I default to the node voltage. So I like node voltage. But you can use whichever techniques you like, and all of them can still get you to the same answer. So just KCL, KVL, loops always end up taking a little bit more algebra to do.
Can we do this without node voltage, knowing what we know right now?
Yep, so to solve this with what you know, you would have to take, you would take a KVL through the smaller loop in the middle, so through the 0.5, 6 volts, and the other 0.5, so you would have one KVL loop there. You would have to do a KCL summation on the left and a KCL summation on the right. And then you would have to algebraically solve all those. So yes, you could set it up. You could set it up still in a matrix form with those equations. And also get that. Actually, I think you need to do a KCL. Yeah, and then you would need another KCL in the middle. Because you would have 1, 2, 3, 4. And then you would also need to use that voltage difference loop. Because you have 1, 2, 3, 4 unknowns. So you need 4 equations. 1, 2, yeah. So you'd have like 5 or 6. And to get, because one of them doesn't, you have to add in an extra variable. So yeah, it would just be more equations to solve. But yes, you can still do it with KVL and KCL. And that's always a backup way of like, oh, let me just check if these answers make sense too. All right, any other questions? Okay, so in your learning material, there's like 2 sections of learning material. One was node voltage, and then the other one was on how to solve simultaneous equations. So that goes through some more examples of solving these equations. So do make sure to look at that. Make sure you know how to solve these and that you get these same answers with whatever tools you're going to use for your next exam. Okay? All right, so we're going to move to another technique which can combine any of the previous ones. Superposition. So superposition, okay, find some. Okay, superposition is just like our lighting system. You have a source that gives you some light. It only gives you that much light on it. If I add in another source, which would be these lights, it adds more lighting to it, so it gives you more brightness. You have another set of source, and this one contributes this much light into the room. So this is basically the demo of what superposition is if I can find out how much light is from each of these sources, they add up to give me the total amount. That's the same idea as current and voltage sources. So if I find a result from one by removing the others out of it, and then I turn off everything else. So for example, I find the light just from this one source with everything else off. That gives me so much light, and I keep that as one answer. I can then find from just that lighting set an answer, and from this one, another answer, and then the total would be the summation of all 3. So that's all superposition is turning off all of the sources except for one, finding an answer, turn off all the others except for a different one, find an answer, turn off each one until you've done all the sources, and then add up their result. Okay? So that's the idea of superposition. It's nice in that it can reduce circuits down to be like, oh, that's a voltage divider, or that's just a current divider. That's an easy equation I can just look at by inspection and say what the value would be. So this is an example, not too complicated of a circuit. So in this example, we're going to turn off one source, leave on the other. So let's start with eliminate the current source. Oh, and we're trying to find I2 here, by the way. So this is what we're trying to find is I2. And so go ahead and turn off the source. So when you turn off a current source, what happens to it? So a current source equals 0. Remember, that's like the little video with the tube that had the balls in it, not connected with anything. The balls do not move out of it, open circuit. So that was what I equals 0 means, an open. So this ends up being our circuit, kind of running out of time. Anybody see what is I2 for this one? Yes.
20 milliamps.
Okay. How did you get that?
I put 100 and 200 ohms in series, so it's 300 ohms, so 6 divided by 300.
Correct. So you just, same idea as what we just did. You know the voltage across both of them. There's only one branch. So V over the resistance combined. So 6 over 300. Is it 2 milliamps? 0.2 milliamps? Okay. So that gives us one answer. Then in this one, we're going to remove the voltage source. What happens to a voltage source when you set it equal to 0? Becomes a wire. And what is this circuit? Current divider, so I2 will be correct? Yep. So R1 would be the opposite branch, so R1 times the 18 milli, and is it plus or minus? It'd be minus. Good job. So minus 18 milli, 100 over 300, which is minus 6 milliamps. And then we would sum for the total. So we had 2 milliamps from the first one and a minus 6 milliamps from this one for a total of minus 4 milliamps. And that is how you use superposition. All right, see you guys. I'll see you in a couple weeks and enjoy the guest lecture.